So now I'm in the picture. Good morning, everyone. I will give this lecture in English because I do not speak your language, but I understand what you are telling each other, that Trafco is a fantastic toroidal transformer manufacturer, and I'm very happy to cooperate with Trafco because together there is a lot of knowledge how to make very good audio transformers. I design audio transformers for many years, and I have a factory in Canada, in Toronto, that is called Plytron, and they are for the Canadian and the American market. I have a factory in the Netherlands, my home country. It is called Amplimo, and they are for the Western European market. And now there is a very good welcome. Now there is a very good cooperation with Trafco, based here in Belgrade. And our transformers are meant for the Eastern European markets, Russia and all the countries around here. The aim of my lecture is I would like to explain the advantages of toroidal transformers. I will not talk about the disadvantages of toroidal transformers. Now, to be honest, that's a joke. I will give you scientific information, and I will be not a businessman until the last sheet. Then I will talk a little bit about business. But first part to come is purely scientific information. So let's go to the sheets, and I would like to point out that the correct website of Trafco is not code Yugoslavia, but is .Republiek Serbia. So that's a misprint on your paper, so you can repair that. What I do in my research, I design toroidal transformers. A little bit I design EI transformers, and a little bit I design very special stepped-up transformers meant for moving coil pickup. But this is a major part of my scientific research and my work. I design them. I don't manufacture them. That's Trafco who's doing it. I do the scientific part of the work. Also, I apply these toroidal transformers in valve amplifiers, like the example here and the example there. And this is also a valve amplifier with old-fashioned EI transformers. But I know the world of transformers, and I know all about valve amplifiers, so I can make that combination. I also write books, and some of my books, there is one, and I see the other one is somewhere over there, yes. They are in my language, they are in German, they are in English, they are in French language, translated. And yesterday we discussed the possibility to let them translate in the Serbian language, or maybe even better in the Russian language, because that will be a bigger market. More news will follow about it. I have a school, it's called Tube Society, and every Saturday morning students come to me and I train them in making valve amplifiers. That is an art, and you can learn by doing it yourself, but it is a lot of help that I give my experience to those students. So that's what I do, and if there is some spare time left, I deal with women or my family or my children, or I play the guitar. That's just my hobby, and that's what I am doing. Okay. Next, as said, it is not a sales story. It's scientific information. I will talk about toroidal versus EI. I will deal with a so-called equivalent circuit. I will show how to apply these transformers in the correct way. And then I go to low and mid and high frequency behaviors. I go to feedback. I give samples of specifications, and I go through the whole history. What is a good transformer and how should it work? This all is purely scientific information, and here I talk business a little bit. So let's go to the first point. When we compare EI transformers, the block ones, with the toroidal transformers, there are huge differences between the two. Let's go and discuss a little bit. In an EI transformer, you always have a little gap in the core, which changes the magnetic behavior. In toroidal, you don't. There's no gap, unless you make one. That's a huge difference. The primary inductance, meaning the low frequency response, is not that large in EI, but is extremely large in toroidal. The current unbalance, I mean by this, suppose you have a push-pull power amplifier. Two tubes are swinging and the transformer is in between. Those two tubes, valves, they ask a quiescent current, and if there is an unbalance, the core of the transformer will have a current that magnetizes the core permanently. So if you have an unbalance in the two currents, the EI says, oh, I'm not so sensitive to that. But the toroidal says, I am very, very, very sensitive to that. I demand in toroidal that those quiescent currents are exactly equal. I will explain later why that is the case. The winding also creates a certain capacitance, all those winding in close to one another, and that's we call the winding capacitance. It is small in EI, but the toroidal, you wind it all around, so that capacitance will be a larger surface. And because of the larger surface, it will have a higher value. So that's also a difference. In an EI transformer, the magnetic field lines should go this way, two ways. And you have sharp corners, and you have intersections, and some of those field lines escape and do not stay in the core. We call that leakage. And leakage is rather high in EI transformers, and is extremely small, welcome, and is extremely small in toroidal transformers because all the field lines walk in a circle. There is no escape path to go into another direction. These two items, the winding capacitance and the leakage, they cause ringing. Ringing is extra high frequency response, and that extra high frequency response can create even an oscillation. Now, EIs are prone to ringing. Toroidal has no ringing. Why? I will explain later. The bandwidth, the frequency range from lowest to highest frequency, is rather restricted in EI, but in a toroidal it is like that. Why? What causes the bandwidth to be so large? In an EI transformer you have the coil on a small former where you wind the windings and then you add the core, and the core sees the windings, so there can be sparking. In a toroidal you wind around the core, you isolate it with a plastic or whatever, and there is no escape path for sparking. Meaning, and that is the truth, I have none broken transformer due to sparking, high voltage leakage, in my whole life. I'm 64 now, and all of my transformers, when they get broke, it is because they break the wires, but not because of sparking. So a high degree of isolation, and the losses in magnet wires, I will explain later, that is the resistance of the magnet wires, are medium in the EI, because you do not have so much space in EI to wind the coil, but you have much more space in toroidal, and that means that you can use thicker wire, a larger diameter, and that means that the losses are less, or low even. In all, EI and toroidal are totally different. They have totally different specs. They have totally different application. So in my next sheets I will explain this for several frequency ranges, and then I will explain the advantages more precise. Let's go to a typical application. We have a valve amplifier, input section, preamplification, phase splitter, power tubes, which are connected to the transformer, and here you can read the name Amplimo. That is my Dutch, Eastern, not that's my Dutch, Western Europe company, but you can read here Trafco as well. That's now the same. These tubes are in balance, they are in push-pull, and the current is delivered here and goes this way to this tube, and goes this way to the other tube. And I already explained that the upgoing current and the downgoing current should be equal when there is no music, the quiescent situation. If they are not equal, the core will get saturated. This is a typical application of an output transformer. Now I wish to study such an output transformer inside. From the outside you can see that a toroidal transformer is much nicer than an EI transformer. It's round, it's in a can, it's very well isolated, and it's not a square block. But that's not what I'm talking about. I'm talking about what is inside the transformer. Now inside in the transformer you have the primary winding and the secondary winding. You have the losses inside the core. You have the leakage, escape of field lines on the primary side, and on the secondary side you have the magnet wire resistance on the primary and on the secondary side, and also you have the primary winding capacitance, the secondary winding capacitance, and a kind of coupling capacitance between the primary and the secondary, because they are close to one another. Only in toroidal transformers, because it is very straightforward how to build them, you can replace this large equivalent circuit by a much easier circuit. And then you say, I have my loudspeaker connected, I have the wire resistance of the secondary, you have the wire resistance of the primary, you have one leakage, you have one winding capacitance, and you have one inductance. And when you study this schematics, you will think that the tubes are here driving with their plate resistance this circuit. And this circuit will act as a filter. At high frequencies, this winding capacitance will block the frequencies to go into the transformer. At high frequencies, this leakage will block as well the signals to go into the transformer. And at low frequencies, this inductance can shortcut the energy to go into the loudspeaker. So this schematic is simpler, but it is enough to explain the frequency behavior of a toroidal transformer. When you have EI, you must use this. When you have a toroidal, you can use the simpler circuit. Well, let's talk about, you have bought one of my toroidal transformers. You are planning to build an amplifier. And the first condition is you must guarantee that the two quiescent currents of the two valves are absolutely equal. Better than 1 milliamp equal. How to do that? You can trim the valves to be equal, but half a year later there will be a little shift because of the aging of the valves. So if you wish to have a continuous balancing of the quiescent currents, then you can use a current source at the cathode of each valve. Each valve gets its own current source, and then you guarantee with only a few transistors that the currents are equal. Or you can buy an auto bias circuit, which I designed. It's rather expensive, but it works fantastic. It controls the tubes being equal between 0.1 milliamps. But this is a very important condition. When you use toroidals, be absolutely sure that the quiescent currents are equal. If you don't do that, then you get a nasty mistake, which I explain with these measurements. The nasty mistake is this. Here I have a graph, and the vertical axis tells me the gain of the complete amplifier. So, how much output voltage divided by how much input voltage. That's the gain. And the gain is expressed in decibel. And I make this measurement for the input voltage rising, and I research the gain if it is a constant. I do that for 3 or 4 frequencies at 1 kHz, 70 Hz, 20 Hz, and 10 Hz. And now, for instance, this is a 1 kHz measurement. Gain is very constant. This is 70 Hz. Gain is disappearing a little bit. This is the 20 Hz measurement, and this is the 10 Hz measurement. And you see, in this situation, that the gain for rise is not a constant with frequency, because here you lose the base, and that is caused by non-equal quiescent current. If you have absolutely equal quiescent currents, you see the gain stays a
constant. Only at 10 Hertz here you get saturation at maximum power. So this is a saturation situation, but the mistake, as we see here, it stays equal, so it is correct. That means that the base response of a toroidal transformer is very firm, very powerful. What is the cause of the disappearing of the base when you have unequal quiescent current? Well, this graph tells about what happens inside the core. You have all those magnetic domains, the Weiss areas, that is the official name. They move with the sound. But when you apply very little power, here you have large power, and here you have very little micro power, those magnetic particles tend to stick to one another, like a kind of glue. They do not wish to move. And as a consequence, the permeability, the movability, gets much lower at low powers. At high power, there's no problem. But at low power, they will not move that well. As a consequence, when the particles do not wish to move, as we saw here, when they are directed a little into one direction because of the unbalance of the currents, the permeability disappears, and you cannot hear the lowest frequencies, and you cannot hear the micro details, because this is very low power. Here we have the micro details in the sound, like the wind, the birds, the rattling of the paper or whatever. You cannot hear that. So I say it once again. If you apply toroidal transformers, please make sure that you have absolutely equal quiescent currents. It's very important. There is another possibility. Thank you for the music.
I apologize.
Nah, that's no problem, I understand.
I forgot to switch off.
Yeah, there is always a woman who wants to talk to you. Okay, be quiet a bit. To have as much good quality low frequency, what is a very good design method is using triodes. And when you use triodes, you have a low plate resistance, and then I will go back to one of my earlier drawings. When you have low plate resistance, this resistor disappears, this capacitance has no influence anymore, and you can very firmly drive the primary inductance. So one of the rules, and that's for every transformer, not only toroidal, try to make the plate resistance of the driving valves as small as possible. There are several methods. I will show them to you. Oh no, I'm missing a figure now. Let's see where it is. There are several methods. You can normally drive the output transformer with pentodes, or you can apply tapping, which we call ultralinear feedback, or you can make the screen grid to the anode and create a triode, or you can apply cathode feedback through windings, or you can apply feedback over the valves. All of these methods are very important to lower the plate resistance of the driving valve and to make the bandwidth larger. In general, I can state, and this is true for all transformers, a good transformer asks for low plate resistance drive using large tubes, using large transformers with no internal losses, balancing the quiescent currents. This is true for EI and this is true for toroidal. So where is the advantage of toroidal transformers? Why to spend money on another device? I will explain you this now. The true advantage of a toroidal is at high frequencies, because a toroidal has almost no leakage, and that gives a tremendous expansion of the frequency range. All the field lines stay inside the core, and with EI they can escape, and that restricts the frequency range. This is an example of an EI transformer with a leakage of 19 millihenry. It's a normal value. And this is an example of a toroidal transformer with a leakage of 1.3 millihenry. That is normal in toroidal. Let's see what happens. In EI you get ringing. This is the frequency and this is the gain. You get a ringing, say at around 40 kHz. And then the transformer collapses. With a toroidal you get no ringing and you get an extra frequency range with a -3 dB bandwidth, almost up to 200 kHz. It stays absolutely stable. This is a huge advantage in a toroidal transformer. You can also study, and that's a different way of talking. I will explain that on the other board. So, Mr. Cameraman, I go to that board. Suppose you have an audio signal, something like that, a burst signal, as we call it, which is going into your amplifier. It's like musical drums or a bass or a guitar tone. It's a burst of energy. This burst of energy contains frequencies starting at, say, 10 Hz up to 40 kHz. All the overtones is in one burst. Now, suppose now that the amplifier, which is here, says, okay, thank you for the burst, but low frequencies have an advantage to pass, and high frequencies I will delay because of the leakage. What will happen is that the low frequencies will start first, and then the high frequencies will come in. And I hope that you can see that this figure is totally different from this figure. What happens, and now I go to that place again, for Mr. Cameraman, is here I have the delay, or we can also call it the phase of the signal. And here I have the frequencies. In an EI transformer there is more delay in the low frequencies, and then up to high frequencies you get a very strange delay, causing the overtones, the highest frequencies, to be delayed more, and they are not in time. That means that the sound quality, the color of the sound, or the impact or the burst, it contains the frequencies, but it is not in the correct time, and your ear can hear that. That is not the case in toroidal transformers. Up to 100 kHz, every signal is correct in time and is delayed, every signal in the same manner. So this burst you will also see at the output of the amplifier. That's the reason of this graph. That has two advantages. You have wider range, you have no resonance, you have a cleaner and more detailed sound response, and you can apply feedback if you wish to clean the sound without creating extra oscillations. You know, when you apply feedback in a valve amplifier, it can start to become a transmitter. With toroidal, the chance to build a medium wave transmitter instead of an amplifier is much lower. You get an amplifier and not oscillation. When you apply feedback, that is, you compare the output signal somewhere to the input signal and you check is it equal or not, and if it is not equal you correct that. That's feedback. When you apply feedback and you do that with a toroidal, then as said before, you get no oscillation. When you do it with EI, you get very soon oscillation around this frequency. To prevent oscillation, to make the amplifier absolutely stable, please go to, and I already explained that, from pentode to ultralinear to triode or cathode feedback or unity coupled or supertriode circuits or combine all that stuff, because when you make all those kinds of combinations, like here for instance, I have cathode feedback and I have ultralinear tapping. When you do that, you make the mistakes of the tubes combined with the transformer smaller. Not by total feedback, but you do it on a local level, only between the power tubes and the output transformers. Meaning, the distortions here will get small. Meaning, the bandwidth will get large. Meaning, the damping of the loudspeaker will get better as well, so your bass response will improve. As said before, this is valid for all type of amplifier and transformers, but doing it with toroidals will create no oscillation and your amplifier will stay stable. There is another advantage. Suppose I have built an amplifier, it has a gain which is far too much, 157, and I only need, say, 22 times of gain. Then I apply feedback. This was the bandwidth of the amplifier, up to 20 kHz, and when I wish to apply feedback, I get this bandwidth once again, but I need a trick to have a stable situation. I have to build in an extra filter, and when you apply feedback, this area tells you how much the feedback is able to improve the signal. And you see from 4K up to 20K, there is growing less amplification. to improve the quality of your sound. You improve for low frequencies, but that gets worse for high frequencies. Now take a toroidal. Same situation. All the audio frequencies are controlled in the same manner up to 20 kHz, and the less improved is above what you can hear. And you can do this trick because the bandwidth of the transformer is so huge. In this way, you are absolutely sure that you improve the quality of your audio signals equally compared to EI, where 20 kHz is here and here 20 kHz is here. You have less improvement the higher you go. So, also in terms of overall feedback and overall control, the quality of a toroidal, due to its large bandwidth and no ring, allows you to apply feedback in an equal manner for all frequencies. That's impossible with standard EI transformers. Now, let's talk a little bit of the range of transformers we have at Trafco. There are all toroidals. We can have push-pull. And at this moment we have a range, I think, Krista, from 10 watt to 100 watt. That's our range, let's say that. We have a primary impedance from 1K to 8K, and all the tricks of local feedback, UL taps, controller feedback windings, screen grid windings, they are standard available. We have that in our standard program. But suppose you want to build single-ended amplifiers, then we get the core, we cut the core and glue it very precisely together once again. We have powers from 10 to 90 watts and primary impedance of 2K5 to 9K. That's all in our standard program. And we have also special transformers for headphones, for electrostatic loudspeakers and so on. Just visit the website to see the program. All those transformers per piece come with very precise specifications, like the frequency range, like the phase behavior, and like the time, differential time delay behavior, and all the important numbers. I'm not going to discuss this, but you will see we tell the winding resistances, we tell the inductances, we tell the leakage, we tell the capacitor, and so on. Try to find another company who gives so much information. They mostly give the ratio, the impedance, and they probably will give you the power, and that's it. But we tell you much more to enable you to check the transformers, to do calculations and whatever you wish. And when we deliver, these figures are all correct with a little bit of deviation that might go 15% up or 15% down. We guarantee that. So very precise specifications. Now finally, I will talk a little bit business. I'm a scientist. I am not a businessman. So I know nothing about pricing. I know nothing about manufacturing. That's not true, but for here I know nothing about it all. Suppose you say, I would like to build a very high quality, high-end valve amplifier, and okay, I believe you, I will go to toroidal transformers. What happens next? Tell us please what you need. Then personally, Menno, with my experience, I will start talking with you and I will derive the specifications that you need. Then, based on that, Trafco will give you a price quotation. And based on that, we will build one prototype, or two for stereo if you wish, that you can check very precisely. At that moment, you can say two things. Probably you will say fantastic, high quality, or maybe, and I've never experienced that, garbage. So we are a little bit in business because it is high quality and so on, and then the production can start. This piece, I am involved. On personal basis, you can contact me and through Trafco, and I will support and I will help. This piece, I'm not there anymore. It is Trafco who makes the transformers as specified. This is my story. It's only a short introduction, but I hope to have explained a little bit. Thank you for your attention. If you have any questions, you can put them now to me or later. Are there any questions? Yes.
C course.
Yeah.
What do you think about C course or double C course?
Yeah. I will answer that question when the camera is on my face again and then. So, yeah, we have to make a video recording, we have to. So the question was, what do you think about C course? I have three remarks. Excellent, but they are larger than toroidal. So you need more iron. Excellent C course, but they have those parts glued together. There always will be a little bit of a gap. And that gap can be an advantage, but for the low frequencies at the same time can be a disadvantage. It depends on the design, on your specifications. And thirdly, that little gap of the two C's joining together will create leakage. Field lines will escape. That will limit the high frequency range. It is better than EI, but toroidal is even more better. So that's my answer to your question.
Okay, thank you.
You're welcome. Are there more questions? Yes.
I got one question. This is rather a scientific question. What is the limit of the core itself, disregarding leakage inductances or what kind of impedance we have in primary or secondary core? Or how do you choose a core for this or materials for that core?
Yeah. Okay, the question is, in summary, tell us please a little about the quality of the iron in the core and so on that we are using in our toroidals. The answer is this. I went to the famous German factory ThyssenKrupp. I went to the research department of ThyssenKrupp and asked them, please, what materials do you have available so that I can check the best quality for audio transformer application? And ThyssenKrupp was very helpful, and they gave me samples of several materials, and I selected the best. It happened to be the newest material, but I selected the best. And in terms, I will make a drawing to explain that to you. One of the most important items is the permeability graph versus the flux density inside the core. This is very low flux density and this is close to saturation. And what you wish to happen is that the movability of all those small particles is optimal at all frequencies, at all flux densities. Now, the material that we are using now behaves like this. Saturation. It stays very high even at low flux density. If you, for instance, have a non-good, forgive me what I'm saying now, Chinese, cheap steel, then you get something like this. Meaning, don't ever think that you can hear micro details, small signals. They will be weakened in a terrible way because those magnetic domains will be glued together. At high powers, the core losses and the humming of the core will become severe. The core will eat the energy. This material, we have an agreement with ThyssenKrupp. We will not mention what material. We will not compare to other materials. We will not say amorphous is better or glass iron is better or whatever. We have access to this high quality steel with the agreements with ThyssenKrupp, and we guarantee this quality. Did that answer your question?
Yes. Did the core have some frequency limitation, upper frequency limitation? How much can go up to 1 megahertz?
Yeah. Okay. When the camera is on my side, I will repeat again. The question was, when we look at the core, now not in the low frequency, but at the high frequency range, what are the limitations? Of course, the limitations are always the internal winding capacitance and the leakage inductance. But suppose we make them very small, like in toroidal transformers. When do we get in problems that is around 1 megahertz? Around 1 or 2, because then the core losses will become dominant. So don't try to use this core steel around 10 megahertz or even higher. Then you have to go to farads. But I can guarantee that up to 1 megahertz you have no problems caused by core losses. Did that answer your question?
Yes.
Okay, thank you very much. Are there any more questions? No, then ladies and gentlemen, Maria and Mira and all those gentlemen over here, it was a pleasure to have this lecture for you, and I hope it has been a little bit helpful. We will stop the demonstration. I will stop. Thank you very much.